Okay, so this is, we'll call it Lab 2. Yeah, first one, you know, just because there weren't any cables doesn't mean it wasn't a genuine lab. All right, Lab 2. This is the Speed of Light lab. And I was going to just walk you through, how everything works, but there aren't too many cables for this lab. So this may not be the case every single week, every 2 weeks, give or take. Because some of these experiments will be kind of spaghetti monsters, and I may not have the time to do a video, explaining to you how everything works, but just kind of covering my bases there. All right, folks, a little bit of a break here in that video so that we can explain what the heck is going on. There's actually, well, there's about even components between the speed of light lab and the interferometry lab, but this one's a little bit more, a lot of cables. Let's just figure out what we're doing before I start, explaining to you all those components there. So essentially what we're doing in this lab is we are firing a laser. It is going to bounce off of a mirror, and then it is going to hit a detector. The oscilloscope, which is the first thing we're going to start talking about, and in just a moment in the video, I'm going to go left to right and explain all the things that are going on in this lab setup. This oscilloscope is basically a very, very good stopwatch. And so this laser is going to be, well, I'll, walk through all the cable connections for the power supply. There's a few little components missing in here in this part of the thing. I just wanted a very, very kind of basic figure right here. So this oscilloscope will measure when the laser fires. The laser will fire. It will travel to this mirror. The bulk of the lab is really aligning this mirror so that it bounces off the mirror safely. There's quite a bit of safety things that we'll be talking about in a minute in this video. It will hit this focusing lens, which is quite frankly very pivotal, as you'll see in the video shortly. If Because the laser comes out here and the detector is up here, and this mirror is very poor. It's not a good quality mirror. It really only angles things in a not helpful way for this lab. It only angles things down, just to, give you a brief little heads up about what that's about. So we need it to be angled up, which is kind of opposite. So ultimately what's going to be happening is the laser light is going to be more or less hitting very, very low on this lens here. But because it's a focusing lens, it will kind of raise it up a little bit, just enough to hit that detector. So what are we doing? I mean, it's basically just the definition of velocity, the change in distance and the change in time. The distance is our independent variable. What we're going to be doing in the lab is moving this mirror to different distances. And the time is what we're going to be measuring from the oscilloscope. So not really too much going on here. Let's see. I think that's pretty much covered here. 2L, because we're going, there and back again. It's leaving the laser, hitting the mirror, coming back. That's going to be our independent variable. That's what we change. And T is our dependent variable. That's what we're going to measure. So based on the way that I've said that, time is the independent variable, time is the dependent variable, length is the independent variable. If we were to try to plot this as a line, y equals mx plus b, which of those is the independent, right? X is always independent, y is dependent. So how can we make this equation, right? I mean, of course, that v is going to be replaced by c. We're working with the speed of light. We need to rearrange this equation so that it looks like y equals mx plus b. So that's what I mean by linearize our velocity equation. Map it onto something that is dependent variable and independent variable. Just kind of including this for everyone's reference. This is more or less everything that's not included in that diagram above. But here's our oscilloscope, here's our laser, here's our detector, focusing lens, and mirror, and then some devices, kind of crude ruler situation over here that I've got to set things up. But this is more the future of that video, what we'll be seeing in just a second. So I'm going to rearrange this a little bit. I'm starting with this equation right here, just writing it as C. And then I'm going to bring my T, because that is my dependent variable. That's what changes depending on what I set the length to. And then making this look as similar to y equals mx plus b, I'm just going to factor some things out. So if I plot length on the x-axis and I plot t on the y-axis, the slope of that line will be 2 over c. And then I can just solve slope equals 2 over c for c.
basically 2 divided by the slope. Okay, so now I'm going to pause this kind of theory intro to come back to this in just a second. So I'm going to pause this part of the video, kind of splice it in, and then come back to this in just a moment.
But for this lab, first things first, let's just go left to right here. We've got our oscilloscope. The oscilloscope is something that's basically, it's really just functioning as a very, very accurate stopwatch. Really, is what it's doing. So let's plug that puppy in. And then let's do step by step. Let's do these 2 cables. These 2 cables are 2 types of BNC cables. This is the regular BNC cable, good for electrical stuff. I'm going to plug this into channel 2. And this is going to be my fiber optic BNC cable, better for light sources. So this is going to be for my laser. So let's head over to our laser unit over here. Plug this in. This red box right here is my laser. And I'll turn the camera around in a little bit to show you where the laser comes out of, and that's where we'll talk safety and things like that. I'll plug this in. So now my laser is powered. If I want to turn my laser on, I turn this key, and the light will start blinking. As soon as the light stops blinking and it's shining on, that means the laser's on. Okay, so my laser's powered, but what about this thing? This is my detector. And again, I'll turn the camera around to show you where we're aiming, you know, with all these mirrors and focusing lenses and things like that. But let's just go, you know, left to right here. So this is being powered, correct? Right? I just plugged it in. There's a blinking light. This is definitely being powered. This, much like you know, if you are a gamer or I mean, look at all these insane gaming computers. We're all gamers now. Sometimes adapters need power. So much like this is a detector, and so it needs to be powered in order for it to detect things. And so you see, you can actually hear, I just heard an audible click when the light went bright pink. So, firstly, this cable now is going to be, we'll go ahead and turn our oscilloscope on. We're not going to be measuring anything just yet. I'm going to put this in here. And now the oscilloscope will have information about my laser. The reason we use a fiber BNC for a laser is just because it's light being transmitted instead of like an electrical signal, like over here. And if you'd like to stare at it while I do this, those little yellow lines are my laser detection. You know, it's a AC power source, so it's just going positive and negative. Now, I'm going to put this over on this side of my detector. I believe it's right there. It's kind of tricky to get on. You just push and then turn. Okay. So now I've got all those set up, and what you'll notice, let's just get some of these cables out of the way. I'm not seeing any. It's just a flat line, right? My detector's not doing anything. It happens to be, well, we'll get there. Even if my whole lab setup at the moment, I flipped open my little safety gate and the laser was bouncing off the mirror and going through, I still wouldn't see anything because this needs to be powered. As when I bring the phone around, I'll show you, but this red button, or kind of input port for a banana cable, that's going to be our first set of banana cables, says 5 volts on it, and the other one says ground. So that means I need to supply 5 volts to this thing or it's not going to work. So that's where I'm going to go over here, put that in my negative terminal, put that in my positive terminal, put that right there, put this right there, and then I'm going to turn on my power supply, which is not plugged in. That button, don't want it to blow up or anything. Okay, let's put this here. Actually, that may block my visual of the oscilloscope later. That's okay, I'll change the camera angle later. It would be silly to assume that I can do this all in one take, as they say. Okay, so now I'm going to turn on my power supply, and it is right around at 5 volts. But you'll notice that, when you start to look at these things, that's a pretty bad scale. And actually, what I'll show you on the oscilloscope a little bit later, the voltage that you supply to this thing changes how you detect. So if for instance, if I supplied this unit with 4 volts instead of 5 volts, I wouldn't detect the same thing. So in order to make sure that I'm giving it its proper voltage, I'm actually going to add something to this, which I don't believe was in the lab manual, but, well, lab manual. Ground to COM, red into here, turn on the voltage, and it looks like I am at 5.1. So that should be pretty much okay, but we'll turn it off for the moment, and we'll circle back to that when we get to, results and things like that. Okay, so at the moment, we are pretty much all set. We have all the cables necessary for the experiment. So I'm going to pause right now and get a little bit better camera angle. Well, actually what we can do is, you know what, before we even talk about, moving the mirrors and things like that, let's talk a little bit of laser on this angle and safety-wise. All right, I will be completely honest with you. I didn't even know that iPhones could pause video. That may be a result of me just getting a new phone because Verizon is really hurting for customers, or it could be that I just don't know how to use it on camera. Okay, so laser safety time. This little, note the 5 volt ground. This little gate opens and then the laser comes out. Okay, so now my laser is coming out of here, going to my mirror, which I'll show you in just a second, and shooting back here. So a few kind of safety measures that I want us to practice. I'm gonna try to find some laser safety goggles in the other room for everyone, but just in general, I would say, looking into that, I don't even think I need to mention, that's kind of the one where everyone is, it's like not looking down the barrel of a gun, right? Everyone pretty much knows not to look there. But what I want everyone to be really careful about this semester is, what if someone walked over there? If that laser wasn't touching the mirror, let's say I was, doing my adjustments and such, what if someone walked by and they happened to, the laser does not have to hit you right in the cornea for you to have laser eye damage. So I just want everyone to be sure. We have relatively large lab groups. Really just want to make it really, really important that, at least, maybe you don't have to delegate someone. I think it could be a good idea to delegate someone in your lab group as the safety person, especially when you're working with lasers, which, quite frankly, the first few labs do. I haven't prepped every single lab so far this summer, but at least the first two that I'm making videos on today involve lasers, high-powered lasers. So I really want to stress that this is the real deal. Okay, so how does this lab work? I will splice in my kind of theory intro, but essentially what we're doing is we are using that very, very good stopwatch, the oscilloscope over there, to measure how long it takes for the light to come out of that laser, hit this mirror. Again, I'm being careful here because now, as soon as my hand is touching this mirror, now the mirror is the laser source. So now I have to think, is there anyone over there? Because you can't see it on camera, but as I'm doing this, unless it hits the detection box, it's now on that computer over there. It's on the wall over there. So there's as soon as we start messing with mirrors, especially this lab where you can really, if I did that abruptly, I would sweep. You can see I don't know if you could, you probably can't see it on that video, but I'm sweeping a laser across the entire classroom. So it is very, potentially dangerous to just be, willy-nilly. And I mentioned that in the theory. I'll get back to that a little bit later. Okay, so now that safety aspect of things has been discussed, let us talk about
when that's going to come up because there is a part in the lab where you aren't really going to be putting the mirror on a lab jack stand. You're going to need to hold the mirror with your hand. Um, you don't necessarily need to do this part of the lab. It does help you get a feel for what's going on, though. So I would recommend it. Just be very careful. So this is a part of the lab where you're going to be bringing the mirror as close as possible. But now that you have seen at least a little bit the issue with the two devices being stacked up on top of each other, there comes a point where you can't bring the mirror any closer, at least if it's on the lab jack stand. And so in this case, what we're going to do is take it with our hand and move it very close. So what are we doing in that context? The reason this is there, right? Why is that just not zero? And what I mean about the lab manual gives you um, a little bit about this. I believe that is down here. So this is what I'm referring to, right? This. So this is what we're going to be talking about right now, the delay time. So what you'll find is that if you hold the mirror as close as possible to the laser and like angle it upwards, again, here's where that safety part of the video that I just paused at is important because now it's not even on a lab jack stand. It is entirely in your hand. Maybe even use two hands. If it's just in your hand, so that means any small adjustments in your hand are gonna, now your hand is the laser. So what you'll find is if you bring it as close as possible, there's like a finite limit. So just to give you some ranges of numbers, it's roughly in the like anywhere from 30 to 60 nanoseconds is roughly what you're going to be seeing throughout the lab. However, if I were to bring the mirror very, very close, I should see that the time is almost zero, right? If I bring the mirror almost right next to the laser and shoot it up into the detector, the light isn't traveling very far, and so it doesn't take very long to do that. However, that's why we have to include this B, and that's what you'll see. It doesn't get below roughly around 30. Why is that? That is because it takes time. Here, I'm talking about, carefully about this. You'll find, let's see, is there anything I can, no, I literally just said all of that thing. So just based on like some dimensional analysis here, this is what? This is a length, and then we divide it by a velocity, so that gives us a time. This is a time. So what is B? B is another time, and it has more or less a minimum value. It will not go beyond that. So what you'll find is as um, this laser is like orders of magnitude. Let's see, what am I saying here? You'll find that even though the light is going orders of magnitude less distance. Oh, right. So like if you put your mirror a meter away, but then you bring your mirror centimeters away, orders of magnitude difference, what you're going to find is the time it takes, at least the time that you are measuring, this time t, it's not actually going to be that different. It's like 30 versus 50. That's the same order of magnitude. So what's going on here? This is where the lab gets you to start thinking about this a little bit. However, the lab doesn't, this lab manual doesn't give you everything. It says, consider the fact that light takes about 1 nanosecond or 1 nanosecond to get through about a foot of cable. And so if we look back at our kind of setup, do I have the wire set up yet? Yes. So I've got a fiber optic cable because it's fiber, that will not add any time, but I've got maybe 1, 2, 3 feet here. And that's just powering things. So technically, this B value, at least based on what the lab manual is telling us, it should be about this. A 3 foot cable adds about 3 nanoseconds of time. That B value that you end up finding is going to be more like 30. So my question to you is where else is that time coming from? Um, Obviously it's more or less entirely in this section of the lab setup, but I just want you to think about like where that could be going. are there things we don't see, right? This oscilloscope is, for our purposes, really like a black box that's a stopwatch. Of course, we're learning how to use it and things like that, but there's a lot going on inside there that you may have some ideas about to try to get an idea of where that kind of minimum time is coming from. All right, back to the instructions for this.
Okay, so I mean, yeah, what is our independent variable here? Distance. The way that we're doing this lab is I personally, because the laser is actually right at the end of this lab jack stand, and it's actually bolted to the lab jack, so you don't have to move it. It's more or less, I would say maybe half a centimeter beyond that. But also there's the lens housing, so let's just say that the lab jack is 0. And then what I'm doing is I'm just using this little stick, because the mirror, as long as I keep it right along the edge, this one isn't bolted down, and I haven't found any two-sided tape around here yet. So I'm just going to say, I'm moving my lab jack on the mirror, at least until I do some spins. And so I'm going to, and what you'll see in the theory where we talk about the time delay and things like that with the oscilloscope and things like that. As I start to show you how to do this alignment, you'll notice that I can't really get anywhere closer than around 45 centimeters. Just based on the fact that these two components of the lab apparatus are soldered together, or well, they're just mounted together. In theory, we could take that off if we wanted, but it's kind of annoying because that means we have to use this mirror, which actually doesn't have an angle up feature. It just has an angle down feature. So that means this is being shot at something that angles it down. So this focusing lens is really just going to save the day for us. Because as long as we hit that lens somewhere, it will raise up our beam just a little bit. So let me show you how that works. Right. This is a pretty good meter stick. It's very well marked. So I would say down to the millimeter. And then based on these lab jack things, I'm going to add maybe another millimeter to that. So I'm going to say my uncertainty is like 2 millimeters. And that would be my uncertainty in length, of course. Oscilloscopes, we can look up, their time uncertainty. But as you'll notice, once we start looking at the oscilloscope data, it's a little bit, you don't really have to go looking very far to see where the uncertainty is there. Okay. Because of the height difference, right, I'm going to, if I raise this up a little bit, spinning my thing, eventually the laser is going to hit my lens on this side, and it's not going to hit the mirror anymore. See, it's not hitting the mirror. If I lower it a little bit, you'll see the red dot right there. So this is kind of this is really the hardest part of the data taking for the lab. So let's just set it up here. Actually, I'm going to pause it until there's not much value. I'm sure there's a little bit of value. And if not, maybe I'll become a video editor for this course, because I think this pre-lab YouTube stuff is kind of cool. Okay, so I am going to, actually let me show you what I was talking about with this. This knob would push the mirror that way, so angle it down, and this knob back here angles it that way. So really the best thing that we could do is move the mirror that way, move our lens a little bit this way, because ultimately that black circle right there, I'll give you a little zoom in on it, and I'll get it much closer when we're finally getting the laser in there. But it's kind of tricky. This is a tricky little process. At the moment, my laser is effectively going under my lens because I can see the red dot right there. So what I'm going to do, because that red dot is almost into the lens, I think I will be okay as long as I move the red dot as long as it hits, like I said, as long as it hits the bottom of that lens, I should be good. So if I use this knob, I think I may have it. This may not take as long as I thought. Oh, we're seeing something. There it is. So notice, I'll show you in just a moment. My red dot is hitting, I mean, just barely. Just barely. Let's see if you can see it. Yep, there it is. Just barely. But that's all I need. And so now we have to notice that this lens has a focal length. I believe it's marked on here. Yes, 10 centimeters. I found it's actually been a little bit different. I was getting 7 centimeters to work quite well. Don't know why I'm on 0.5. So what I'm gonna do is I am going to, in order to find the focal length, the easiest way to do this, notice how there's, let me zoom in a little bit really close for you. See how there's that arc? There's kind of a dot and an arc. As I move this away, actually now that I'm getting closer to the mirror, it's not, it's getting onto the lens, but let's see if I can show you. There's a little bit of an arc. As I get closer and closer to, I've had a lot of success around 7 centimeters. Let me show you what happens to this as I get closer to the focal length, and then I'll go beyond it. So I'm getting closer, and the arc is decreasing until it looks very point-like. And then if I get closer, the arc starts to form again. See that? So I don't want arc. I want all my laser in a point. Kind of like that's as close to a point as I think I can get. And lo and behold, yep, that's pretty much 7 again. About 6 or 7. So now I just need to start fiddling around with this until I can get that dot to be inside that detector. See that little, black dot within that black square? So now what I need to do is, honestly, this thing, moving the lens, has been the easiest way to go about this. Making sure that, and you can use another little piece of wood to maintain the focal length that you found. Right around there. It looks like it's around 6.5. And I'm going to move it left and right until I can, and here, because we know where the laser is going, right, we are not touching the mirror anymore. We are only moving this lens, which is going to have a minute effect on that little red dot. So I'm moving, and I'm going to kind of try to center myself above this thing so that I can see when it's left and right, centered on that black dot. That looks pretty darn good. And now I'm just going to twist the knob on my lab check. And I'm actually, as I do this, I'm going to make sure the oscilloscope is in view. So, yep. So y'all can see what's going to happen as soon as this laser gets in that hole. All right, I'm going up. Once you get to this part of it, it's quite hard because now, you really don't want to look into it. But it has this kind of, virtual image effect where you're not seeing it bounce off the walls. That's really what I'm looking for. That looks pretty good. I'm not seeing it on the surrounding kind of housing of the detector. I'm just seeing this kind of virtual image of the dot. Okay, so now let's go look at the data and we'll explain what we're looking at. All right, so I am going to clear some of these measurements so that I can walk you through how all this works. Let me remove measurement 1, and let's say, can I take the cursors off? I don't think I can. Cursor off. Okay, let's just look at everything. Menu off. All right. That's much better. Okay, that's perfect. So my scale is actually way too, there we go. That's actually perfect. Okay, so what are we seeing here? Because this is the laser switching, from positive to negative, let's just call that the laser turning on. It is flipping up. Then this is no laser being shown in the detector effectively. Then you'll notice, let's see this blue line right here. The yellow line. That yellow line is when, time-wise, the laser turned on. And yet this blue detector line is not dropping until then. And when I say dropping, why dropping? It's just based on the way that this device works. It's a photomultiplier, effectively, and that will measure the negative because of the electron. With a high voltage on the negative, I can link some material for that. So that means this time delay is the amount of time it took for the light to go back and forth that distance. But one extra thing I want to do is just make sure that we understand why this 5 volts is so important. So let's turn this on just to make sure we have an accurate reading here. So, it's roughly at 5, but let me just show you. I'm going to turn the scale back down to looks a little better, actually, at least for our purposes right now. Okay, so what I'm going to do is I'm going to start turning down this voltage. If I turn it down all the way, the device doesn't work. It's not being supplied with any power, and so it can't detect anything. As I start to turn this up, we'll start to see some stuff. And what you'll notice when it gets very close to 5 volts, normally around like 4.9, we start to see some stuff. And let me try to get both of these. You technically don't need to see my hand spinning it. You have a voltmeter right there. You'll see a snap, is what I've been calling it on the oscilloscope. There it is, 4.95. So that, to me, is the threshold that we need to supply that detector with, threshold voltage, in order for it to work. So notice, here's the snap again. I'll actually use the coarse knob on the power supply. So I'm getting very close, 4.9. Spin it just a little bit. Snap. And now that looks like good data to me. We can kind of ignore the positive, response spike. Nothing, detecting the laser. And it's kind of hard to see at this point, but it's, once we start doing this scaling on the horizontal, we can see what we're looking for. Laser emitted, laser detected. And so now let's see how, in theory, we could do this with something called the cursor. Cursor's kind of like doing it manually. So actually, it's not even worth showing you that because it's not as effective. So let's do measurement. And so this is the bulk of the lab. Quite frankly, this is what took me about a week to figure out because oscilloscopes are kind of hard. What we're gonna eventually be calling this the rising edge. The rising edge of channel 1, because channel 1, remember, is my laser. And then the falling edge of channel 2, just based on the fact that this is detecting a negative signal when it receives the photon and then is converted into an electron. So when I press delay, what I want is the first, actually this is, I believe I had that wrong. I want to do measurement on channel 1. I'm gonna click channel 1, there we go. Oh, here we go, delay. So I want to do the first rising edge of channel 1. That will be the rising edge of this spiking, the channel 1 spiking. And then I want to do the first falling edge of channel 2. So how do I do that? Measure the later channel 2, that's the rising, and then the blue, notice the blue here, falling edge. I'm going to say collect measurement, and I'm just gonna let you know that's pretty much a good piece of data for 50 centimeters. That's pretty much spot on. But notice, remember what I said about the time uncertainty? It's bouncing all over the place. And so, to me, which one do you choose? I would just say use 0.2 nanoseconds as your uncertainty. It will not stop jumping around, no matter what. You can mess around with this just a little bit and see if it stops. Anywho, there'll be some kind of standard uncertainty here. So let me just show you, just for completeness, how these cursors work. For you to manually do this, we want vertical because we're looking at time. And so at the moment, there is you really can't see it. It's gonna be very hard to see. There is a little, this isn't even worth it. There's a very small, you can see it kind of going along the rising edge right now. Going up, there it is, up at the top. That crosshair. This delta and @ symbol, I'll supply you. I have a document called Oscilloscope Basics that go through this quite nicely. But what we can do here, just to get a rough estimate on this, we can say, let's use our other cursor. Where's our other cursor? Select, I believe. Yes, here's our other one. Now it's coming along the same edge. And there it is, right next to its partner. And what we're doing is basically, I'm just kind of manually looking at the same thing that we just did digitally. So notice if I press select again, here's one of them. I'm putting it right on that edge. And then I'm gonna match that yellow line up with that blue line where it detects the laser. And that 39 point, let's just call it 39.2 nanoseconds is a more accurate measurement of that right there. That delta is telling me the distance between those two lines. Again, I can, I'll send you some more information on oscilloscope stuff. But that is the basics of this lab. I'm sure there will be some questions, and that is what I'm here for. But yeah, all right. 30 minutes ain't so bad. I'll get better at this.